Greetings and welcome back. Today we're going to be having an introduction to functional groups. Functional groups are repetitive small parts or moieties or units of an organic molecule that react in the same way. So for instance, if you have a structure like this, which might be familiar from the last lecture, and a structure like this, we have a name for molecules that have little OHs attached to them. And as it turns out, all molecules that have little OHs attached to them tend to react the same way. Therefore, we group them and call them a specific functional group. So, in order to be able to effectively communicate the general classes of organic molecules, we need to understand the names of these different functional groups. The very first functional group we're going to look at today are called alkanes. An alkane is simply a molecule that has just hydrogens and carbons all in single bonds. So for instance, something like a CH3 followed by a CH2 followed by a CH3. So this would be a 3-carbon alkane. There's no real function to these except for to light them on fire. So this is propane and we can burn it. Functional groups like alkanes, or specifically the functional group of alkanes, has very little function itself. So these more or less serve to be the backbone of all molecules. So I would even say this is not really a functional group at all. It's just it's not even vanilla. Vanilla ice cream has actual vanilla flavoring in it. This has no flavor whatsoever. It's just your sugar and your milk. It's just ice cream with nothing in it. So alkanes look like this in terms of a condensed formula. They're not really any special. We've been looking at these already. The line angle structure would just be that. It's all just hydrogens and carbons with no double bonds, no triple bonds, no anything like that. No oxygens, no nitrogens, no nothing. So these are alkanes. And I'm going to tell you some of the names of these. The names are things that we're not going to worry about right now, but I want to give you a little bit of an introduction to them. So you need to know the names of the functional groups. You need to know that these are alkanes. You need to be able to draw Lewis structures and condensed formulas and line angles. But I don't need you to know right now that this guy is called propane. I will need you to know that very soon. So start thinking about it. All right, so here's how we name these, and they're always going to be repetitive. All molecules are based on the start of a carbon chain. So a 1-carbon chain, which is just CH4, is named methane. That's natural gas and probably a word that you recognize. Ethane is just the 2-carbon chain, CH3, CH3. That's also a little gas that really just we light on fire. Propane, you probably know from propane lighters, gas grills, etc., etc., etc. Propane is 3 carbons in a row. Butane, which you probably also know from lighters because we light it on fire. Oops, it's not CH4. It is CH3, CH2, CH2, CH3. This is butane. That is 4 carbons in a row. All right, this is getting repetitive, so I'm going to turn this into line angle structures. 5 carbons in a row is called pentane. And at this point, we go into the lovely prefixes that you've probably recognized. Pent means 5, just like the pentagon. Pentane is 5 carbons. 6 carbons in a row is called hexane. Note that these don't have any branches or anything. We're just talking about straight chains. 7 carbons is heptane. 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8, is octane. Octane is probably a word you know from gasoline rating. Octane, just like propane, butane, methane, we light it on fire. All right, 9, the prefix is none, so 9 carbons in a row is nonane. And lastly, for our purposes in this class, 10 carbons is decane. Right, so think about a decade as 10 years. Ooh. Decane is 10 carbons in a row. All right, so once again, you're going to need to know these specific names, but what I need you to know right now is the names. These are alkanes, and be able to turn Lewis structures into condensed formulas and line angle structures. There are a few functional groups that I'm going to put together on this slide that are variations on an alkane. They're still just hydrocarbons, so all they have is hydrogen and carbon, but they have multiple bonds. So something that has a double bond, so specifically let's look at CH2 double bonded to a CH followed by a CH2 CH3. So this would be a molecule that looks like this in terms of a Lewis structure. So this is a 5-carbon molecule that is not an alkane because it has a double bond. Any molecule that just has carbons and hydrogens but has a double bond is called an alkene. Only that one letter differs. It's an alkene. An alkene, when you turn it into a line angle structure, one of those bonds, instead of going to be all single bonds, one of them will be a double bond. We would just draw it like that. So this is our 4 carbons in a row. 1, 2, 3, 4. This is 4 carbons in a row. 1, 2, 3, 4. And you can see the condensed structure at the top. 1, 2, 3, 4. As I've mentioned previously, condensed structures have multiple correct ways to do them. Excuse me, a lot of times people will write the structure out as this, CH2CH, CH2CH3. And then you actually have to do a little bit of guesswork or kind of intuiting the fact that there's a double bond right in here. I think that that's a little bit silly. The whole purpose of these is to communicate them, so I will always write them like this. It's easy to put a double bond when you're typing things out. It's just an equal sign. So that's an alkene. An alkene, again, is just a hydrocarbon that has a double bond somewhere. Next is an alkyne. An alkyne is a hydrocarbon that has a triple bond somewhere. So in this case, I will draw out a molecule that has a triple bond right in the middle of a 4-carbon chain. Notice that once again, all of these carbons have 4 bonds and all the hydrogens have 1 bond, and that is an alkyne. The way to draw this out would just be to, instead of having a single line or a double line, include a triple line. And there you go. That would be the line angle structure for an alkyne. All right, again, I don't need you to know the names of these yet, but just so that you kind of start to get an idea. The one at the top, the alkene, is a 4-carbon chain. 4-carbon chain, if you remember, is called butane. Well, instead of butane, this one would be called a butene because it's a 4-carbon chain that's an alkene. The one down here would be called butyne because it's a 4-carbon chain that's an alkyne. This one would be called 1-butene because the double bond is at the very end, starting on carbon number 1. This one is called 2-butene because this carbon first has the triple bond is on carbon number 2. Right? So that's a little bit of an introduction into how we name them, which we'll get into further on in the semester. There are 2 more versions of kind of alkanes, alkenes, alkynes, that is to say hydrocarbons, that have rings in them. One of them is a cycloalkane. A cycloalkane is probably just what you're thinking right now. It's an alkane that has a ring. So I will make a 5-carbon ring that has just carbons and hydrogens. And this guy, if you recall, an alkane with 5 carbons is pentane, and so this would be cyclopentane. There's not a great way to do a condensed formula for these. The condensed formula is officially CH2, 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 and back attached to the original CH2. So it's not easy to type, and so these are kind of silly to do in terms of condensed formulas. But line angle structure is very simple. It just would actually look like a pentagon. So that would be a cycloalkane. The other functional group, which is much more complicated, we'll talk about it a lot more next semester, it's called an aromatic ring. An aromatic ring And there are reasons why it's called aromatic that we'll talk about much later, but the historical reason for that is that aromatic rings tend to smell good. These guys are, in general, most often, 6-carbon rings that have alternating double bonds and single bonds all the way through. So they're a little bit like a cycloalkene, but they tend to have double bonds alternating with single bonds all the way through. You'll notice that each of those carbons has 3 bonds, so each of them would have spot for 1 more hydrogen. There is no condensed formula for this. You could write C6H6, but that's a little bit silly. And so the way to do this in terms of a line angle structure would be just like that. So you would have a 6-carbon ring with alternating double and single bonds. This guy is benzene, and this is the only one that we are going to worry about for a long time. And that is benzene. All right, so that is another functional group, an aromatic ring. So let's move into the the functional groups that have oxygens and nitrogens. On this slide, we're going to look at the functional groups that still only have single bonds, but include oxygens and nitrogens. The simplest one is called an alcohol. The alcohol is the one I did on the very first intro slide, which is that these are molecules that have a single OH coming off of them. I'm just going to do the 2-carbon one, so it would look like this. This would be a correct Lewis structure with all of the dots included. This is a 2-carbon alcohol, and alcohols can all be determined by their name by having all at the end. If you recall, or if you don't, a 2-carbon chain is called ethane, so a 2-carbon alcohol would be called ethanol. Ethanol, you probably recognize. This is the alcohol that people always mean when they say alcohol. It's the only one that we can drink that is, I shouldn't say not poisonous to us, but only sparingly poison to us, and we can process it relatively easy. It's also the ethanol of E85 when it comes to ethanol for gas. We can light this guy on fire as well. But anything that has an OH coming off of it all by itself is an alcohol. So for instance, this guy right here is also an alcohol in terms of a functional group. These two are not the same structure. The actual condensed formula for this would be CH3, CH2OH, which is probably pretty simple. And the way that you would draw this in terms of a line angle structure would be just like that. Again, you might recall that we write our hydrogens when they're attached to oxygens or nitrogens, but we don't draw our lone pairs when we're doing out condensed formulas. All right, the next one is called an ether. An ether might also be a name that you're a little bit familiar with. An ether is a molecule that has all single bonds to oxygens, but instead of having an oxygen attached to a hydrogen coming off the side somewhere, the oxygen is actually between 2 carbons. So this is an example of an ether. It always has something on each side of an oxygen. It's got carbons on each side of an oxygen. So that's an ether. When we're turning this into a condensed formula, it would be a CH3, CH2, O, CH2, CH3, which is probably not too hard for you to figure out. Likewise, if we are doing a line angle structure, just put an oxygen in the middle there. It is really important to note that this is a carbon, this is a carbon. The end of this bond right here goes to the oxygen. Therefore, there's not a carbon squeezed in here. So we have 1, 2, 3, 4 total carbons and 1 oxygen in this molecule. So those are the 2 ways to draw molecules that have an oxygen by itself or just attached to single bonds. Either the oxygen is effectively at the end of the molecule with an H coming off of it, and those are alcohols, or the oxygen is jammed somewhere in the middle molecule with carbons on either side, and that is called an ether. When it comes to nitrogens, we don't really differentiate them that way. A nitrogen compound that has only a nitrogen attached anywhere in the molecule by single bonds is called an amine. So an amine would be something like this. Let's do 3 carbons attached to a nitrogen. We'll fill in all of their hydrogens so they all have the right number of bonds. So this is an example of an amine. It's just a nitrogen or a molecule with a nitrogen with only single bonds. Likewise, this one is probably pretty simple to figure out in terms of condensed formulas and line angles as well. This would be a CH3 attached to a CH2, attached to a CH2, attached to an NH2. So these are basically segmented out the same way that we did them previously. Boop, 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 boop. If we're turning this into a line angle structure, we would have 3 carbons, so starting somewhere and going second carbon, third carbon, followed by an NH2. To give you an example of the names of these guys, the ether that has 2 ethyl groups attached to it, so it's got basically 2 carbon chain over here and a 2 carbon chain over here. This guy is called diethyl ether. And this amine over here that has a 3 carbon chain, well, a 3 carbon chain was propane, but if it's a 3 carbon chain with an amine, we call it propanamine. It's kind of like propane, amine. All right, so let's move on to some more functional groups that have double and triple bonds. The simplest molecules that include both a heteroatom, that is to say an oxygen or a nitrogen or halogen or something like that, and a double bond are called ketones and aldehydes. Ketone is spelled K-E-T-O-N-E, and aldehyde is A-L-D-E-H-Y-D-E, aldehyde. All right, both of these include a C double bond O, but a ketone includes a C double bond O that has a carbon on either side. An aldehyde is a C double bond O that has a hydrogen on at least one side. So you have C double bond O's in both of these cases, except that one of them is always at the end of a chain, because this would be the end. And the ketone has stuff on both sides. So let's fill in some hydrogens. I'll make these as simple as I can. We'll make them both just 3 carbon chains. So you could have a 3 carbon chain that has a C double bond O in the middle, or a 3 carbon chain that has the C double bond O at the very end carbon. All right, the way that we do these in terms of condensed formulas is pretty simple for the ketone. We would have a CH3 followed by a carbon with an oxygen branched off of it. Usually, instead of putting a parentheses around the O, we just write CO. The CO has to be the C double bond O, and we kind of get used to that. So this is something I want you to remember, that when you have a C double bond O, we usually just write it as CO, followed by a CH3. It wouldn't be incorrect to put that oxygen in parentheses, but I want you to get used to the common way of doing it, which is just to write CO like that. If you try to draw this out, so let's say that you couldn't see the actual structure there, and we're given CH3, CO, CH3. If you tried to draw it out, and tried to put the CO in a row, you'd see that there's just not enough bonds to that carbon, and that's why this doesn't work. So there is no other way to do it than a C double bond O in the center there. And aldehyde, likewise, let's do what we can do very easily, which is a CH3 followed by a CH2. And then the way we write this group out at the end, the aldehyde group, is to write a CHO. So a CHO at the end indicates that we have an aldehyde. A CO in the center indicates that we have a ketone. The way that you draw these in terms of line angle drawings is just a double bond O coming off of the middle, or double bond O coming off of the end. Sometimes you will see people write the hydrogen right off of that aldehyde as well. That's perfectly fine. The other way to do it is just this. Both of those are perfectly acceptable, and both of those tell us exactly what the molecule is. All right, there isn't really a very common functional group that's a C double bond N, so we're going to skip that one, but there is something that's very common, which is to have a C triple bond N. So that functional group is called a nitrile. So a nitrile would be a molecule that has, let's just do CH3, CH2, and one more carbon with a triple bond N. So this group over here, this C triple bond N, indicates that this molecule is a nitrile. A nitrile is a molecule that looks kind of like cyanide, but it doesn't act like cyanide. Cyanide is, of course, something very toxic. This molecule right here is cyanide. It has a formal charge negative at the end of the carbon. All right? But a covalent bond attached to some greater molecule, like this guy right here, is called a nitrile. So a cyanide is something very different, even though the structures are very similar. So a nitrile just has that C triple bond N at the end of the molecule. And the way to write that out is we just write Cn. So let's turn this into a condensed formula. We would have CH3, CH2, and then Cn, and that would be it. So this guy right here, the Cn, ends up being a lot like the CO of the ketone. It's just a carbon with as many bonds as it takes to get to the nitrogen at the end. To draw this out as a line angle structure, we would have 2 carbons followed by a third carbon with a triple bond to nitrogen. So you can see that right there in the center, we differentiate that we're switching from a carbon single bond, which we have over here, to a carbon triple bond, which we have over here. So therefore that's got to be that third carbon right here, which is right stuck in the center there. All right, so let's do some names for these. Again, the names are just to kind of get you started. They're not something I'm going to expect you to know for this week's quiz. But a 3-carbon ketone is called an one, and 3 carbons is propane. So this guy would be called propanone. 3-carbon aldehyde is called an al. So therefore this 3-carbon chain is propanal. A 3-carbon nitrile is a propane nitrile, and that's how we end that guy. So this guy right here is called propane nitrile. So hopefully you can see a little bit of the logic of how these names are put together. All right, so let's move on to the last group, which is the functional groups that have a couple different things put together at the same time. All right, we have 3 of these kind of combo functional groups, and it's really important to kind of keep these separate from the rest because there's a common mistake to fall into that I want you guys to avoid. So the very first one we'll do is called a carboxylic acid. A carboxylic acid has something attached to a C double bond O OH. So this has both the C double bond O and the OH, but it's not an alcohol. Remember, the alcohol had the OH, and it's not a ketone or an aldehyde, which had the C double bond O. Whenever you see a carbon that has both a double bond O and an OH coming off of the same carbon, it doesn't act like an alcohol, it doesn't act like a ketone, it doesn't act like an aldehyde. It's its own functional group that is a carboxylic acid. So it is incorrect to say that this is an aldehyde plus an aldehyde plus an alcohol or something like that. It is a carboxylic acid. All right, so let me give you an example of this. Let's do something that just has CH3, CH2, CH2, and then carboxylic acid coming off of the end. So this would be, in terms of a condensed formula, we would have our CH3, CH2, CH2. And then the way that this carboxylic acid part is written in a condensed formula is either as CO2H, right, so this means a carboxylic acid, or there's a second way to do this. Both of these are perfectly correct. Sometimes it's written as COOH. Both of those are perfectly fine, and they both tell us that we have a carboxylic acid there. The way to do this as a line angle structure is, let's do our 4 carbons. 1, 2, 3, 4. Then that 4th carbon has a double bond O and an OH coming off of it. So that would be how we do the line angle structure for carboxylic acids. All right, the next one is an ester. An ester, which is different from an ether. An ester is a C double bond O and then an O, but instead of having an H at the end, it moves on to some other carbon over here. So there's just more stuff attached on that side. So as opposed to a carboxylic acid, which would always have to be at the end of a chain, an ether would always have to be somewhere in the middle of a chain. So I'm going to go ahead and put all of my hydrogens in. We'll make this as simple as possible. And that would be an example of an ester. So it's that same little C double bond O part, but instead of being at the end and just having hydrogen, it would have more carbons on the other side. The way to do this as a condensed formula is very similar. It would be to have a CH3 followed by a CO2 and then another CH3. Or, just like the carboxylic acid, we could write CH3, COO, CH3. The Lewis structure, the line angle structure for this would be to draw our two carbons, followed by our oxygen, followed by our carbon, and note that there's that double bond O coming off of the second carbon there. So that would be our line angle structure for an ester. Our last one, the last functional group, is called an amide. An amide is a little bit like an amine. Oops, there I wrote amine. So an amide has a D instead of an N at the end. And as you can imagine, it has a nitrogen involved. But it's a lot like an ester and a carboxylic acid. An amide is a C double bond O that is followed by a nitrogen. And we don't break this up like carboxylic acids and esters. It doesn't matter whether there's hydrogens or carbons attached to that nitrogen. Whatever's in those three places doesn't matter. This is called an amide. So I will put one carbon next to the nitrogen and another carbon next to our C double bond O. This would be an example of an amide. So this is the part you're looking for. It's not a ketone plus a nitrogen, just like the ester is not a ketone plus an ether. These guys are their own kind of combo functional groups that have multiple things squeezed together. All right, so the way to do this would be to write CH3, CO, NH, CH3. So you can see how we're grouping these. This is our CH3, here's our CO, here's our NH, and there's our CH3 at the end. I hope that it seems pretty intuitive to do condensed formulas from these guys. The way to do the line angle structure will look a lot like the one above. We have a carbon, and then a C double bond O. Then we have an NH, followed by another carbon. So that would be how you do that. So once again, I'm going to give you just kind of a sneak peek into the naming. A 4-carbon chain that is a carboxylic acid. A 4-carbon chain is a butane. So this guy would be called butanoic acid. All right, I'm not even going to worry about naming the ester and the amide. Those two names are quite complicated, and we will save those for next semester. All right, thank you very much. Once again, what you need to know from this is the name of the functional groups. There were alkanes, alkenes, alkynes, cycloalkanes, aromatic rings, alcohols, amines, ethers, ketones, aldehydes, nitriles, carboxylic acids, esters, and amides. And that is 14. So there's 14 functional groups. You need to know the names of them. You need to be able to identify them in a structure. You need to know how to turn them into their respective small parts of a condensed formula, and also how to put them into a line angle structure. Hopefully the condensed formulas and the line angle structures make a lot of sense, but I do realize that this is going to take quite a bit of flashcarding or memorizing to be able to remember the names of all these functional groups, but it is really important going forward to be able to do that. Thank you very much. I'll see you in class. Bring any questions you have, and I'll see you soon. Take care.